Hey guys, welcome to the second video in the practical machine learning series. In this video, I'm going to get a little bit more in depth of how does a machine actually trains its machine learning model. How does it actually train out the best suiting y equals to mx function? Because in last time we talked about that the machine learning model y equals to mx is going to adapt to the best possible function by looking how far is the difference between the current point and the predicted point with the current mx. And then if the loss and the difference between them is really big, then we move that function up by a lot, right? We move the m, or we move the theta 1 up by a lot. But what value does it actually increment by? So that is the question we're trying to explore and answer in this video. First of all, let me erase this. And what we really need, I also have to do something else for this. So, first thing is, if we're doing something like house price prediction, in math class, let's just say in math class, you're trying to model a function, you're trying to maybe using sight to come up with the best fit line. You look at this right here, right? If you were to write it in a really standard equation, you won't actually write it as this should be y equals to 350x. But you wouldn't write it like this. You would actually write it as y equals to 350x plus 0, right? Because that is the standard, y equals to mx plus b. So here we introduced a little bit of variety to our machine learning, to our current understanding of machine learning. There is another value, right? There's another value called b. And by the way, the variables can go on infinitely long, and we'll get to that later, right? And that's something called multivariable linear regression. So there's something called b, and in our case, really luckily, since b equals to 0 actually gives us the best fit line, b does equal to 0. But what if it's not, right? What if it's not? What if the points are actually right here? The best fit line will probably be something like 350x plus 10, plus 100. Now again, based on the loss between the current predicted value and what the actual value is, we're going to shift both of these values. You know, this 350 and the b. Sorry about this. This is the best possible function, but we probably start out with y equals to 0x plus 0, right? Then we're going to move the 0 by, and this 0 by a lot if the actual function is a lot further from what we have thought. But what is the actual value we are incrementing by? This is where gradient descent comes into place. The value that we're shifting this by, based on the loss, is the gradient of the loss in respect to m and in respect to b. So this is where a little bit of calculus comes into play. We need to find the loss. Find the derivative of the loss. First of all, what is the loss? Right now, I'm going to formally give you a definition of the difference between this point and what are we predicting right here. There's going to be a formal definition. Definition for of all the losses is going to be for our function right here is going to be this. I equals to 1 and maybe up to n. Then we have squared. So if you're not a math person, it's fine. What really you can totally ignore about this. This is just calculated the total loss, right? The total difference, and we usually use a j to exemplify the cost of a function in machine learning. We can also call this cost. We can call this loss. We can call this error function. But usually this actually here represents error. By the way. Actually, not by the way, but now moving on to the part that you really need to understand, right? You don't need to focus on this. This is important, but you don't need to focus on this right here. y prime is, I just wrote it with an apostrophe, but you know, it's just a predicted y with our current m and our current b. So using this as an example, right, if we have a y equals to 0x plus 0, then if we input a data point at 1,000, where x equals to 1,000, the y will output 0. But in reality, the y is supposed to be somewhere here, which is, I don't know what value this is. Let's just say this should be 1,000. Let's just say this should be 1,000, right? Then this is going to be the y prime. This is the predicted y value with our current parameters, but this is the actual y value. So based on these two values, how much are we going to shift the actual m and the actual b so that they become more accurate? Again, this has to do with calculus. First of all, I guess let's bring back like a 1 minute review of calculus, right? And especially taking derivatives. If you're taking the derivative of 4x cubed, you'll bring down the exponent here, and the derivative will just be derivative will just be 12x squared. Right, it's going to be nx n minus 1. And then there's also another rule that basically says, there's also another rule called the chain rule. And what the chain rule in calculus says is that if you have a function, if you have a composite function like this, then when you take the derivative of f, by the way, don't confuse this apostrophe with this apostrophe. This apostrophe, I'm just denoting it as meaning that this is the predicted one instead of the actual one. But this right here is like a more formal calculus notation, meaning this is the derivative of that. So this will actually be but multiplied with the derivative of the function inside. That's the chain rule. And those are the only two rules we need to know for what we want to do, for how we want to calculate the actual gradient of the actual gradient that we're going to shift our m or our b by, based on y predicted and the real y. So what is it, right? I'm going around in circles. I'm not giving you the actual math. Now what is it? So let's ignore these two for a second, so that it's easier for us to just conceptualize the derivative. Then the cost or the loss or the error is going to just be this, right? And the gradient that we're going to shift each variable m and b, since we only have m and b, by is going to be in respect to only those variables. The amount that you're shifting the m variable by is not dependent on what you're shifting by the b variable by, and vice versa. How much you're shifting the m by, how much you're shifting the b by, how much you're shifting any variable in your equation by, how much you're shifting the parameter value is going to be solely dependent on the loss itself. So we're trying to get this, and we're also trying to get this. So what are those? Well, using the power rule, let's bring this thing. First of all, let's call this error squared, right? Because the predicted one minus the actual one is kind of like the error, and that's why I was kind of avoiding to call this error here, because it kind of conflicts. And now, using power rule, nx, that the derivative of anything is nx n minus 1, then we're just going to do 2 error 1. But that's not it, because we also got to take the derivative of what is inside of error. Right, and then we can do this one later. I feel like I explained something. Why I was talking about this. I think it should be fine. Comment below if you have any questions. I actively respond to these machine learning questions. I really feel like that I left out something. It's okay for now. Let's solve we know what the error we don't know what the error is going to be, but let's try to simplify this thing right here. Now, question is, what is the error? Again, since we made this into error, this, if we revert it back, is going to be this, right? And then, what is this? What is this? This is just going to be, correct? That should make sense, but it might, a similar confusion I might have here is the interchangeability of variables and variable names. And if you're not having a clear grasp of what is going on, you might be conflicted. And it's partially my bad too, for sure. This m right here is actually the theta 1, right, in our predicted equation. This b right here is our plus b, right? It's all in our prediction right now. These are the ones that we're trying to optimize. But what is the derivative of this? What really is the y prime, the mx plus b minus y? And one thing is that hopefully I didn't confuse you, because this m right here is really the theta 1 and the b right here is that b. These are two variables that we're trying to optimize. M and the b, we're trying to optimize that. Y is the actual value, right? The actual y output that we're mapping to check against to see how accurate our predicted result is. So, if you took calculus, you're going to know that when constants are being taken a derivative, they really disappear, right? If you take the derivative of 13, it becomes 0. Same thing. These become 0. So these are really just wiped out. And then, since we're taking the two with respect to m, wrt to m, this x is the only leftover because m is swapped out. So that is the little calculus right there. So let's plug it back in. This right here is really just x, which means this really just equals to 2 error. What is this right here? Oh, to the power of 1 times x. Right, so I'm going to erase this work right here and write it up here. So there's also going to be another variable because again, one of the early on confusions that I personally had was confused on how you actually take the loss, because I was like, how can you incorporate one function and take the loss of every single variable, right? How can you use one equation to take the loss of like the amount that you should shift the theta 1 by, the amount that you should shift the b by, the amount that you should shift the theta 2 by if there's a second x variable. So that was what grew to me. But the thing is that you're taking partial derivatives, right? You're taking it with respect to m, you're taking it individually and distinctively with respect to b. So what is one for b? Because we already got the one for m. Well, again, it's actually I shouldn't have erased all of the work, but it's again 2 error times, but this time is 2 respect to b error, and then so the solve for this is really equal to mx plus b, right? And since we're taking it to respect to b, this is a variable here. This is not just a constant. But these will be erased, and then b left over is really just going to be 1, right? And that's again just calculus, right? If you take the derivative of 3x, you're going to get 3. So if you take the derivative of b, you're going to get 1, or 3b is going to be 3, right? So it's going to be 1, which means this is just 1. And so I was going to show you guys an actual complete mathematical example of how to compute the error, compute, then using the error and the current m and b values, compute the gradient descent, and then change our current values by that gradient to get a even more optimized function, and then continue to do that. But what I'm going to do is indeed write down the pseudocode for that, so we can implement this later in the next video or the next video of this in Python. Probably Python, yeah. So the pseudocode of optimizing a machine learning function, especially this one right here, is going to be for amounts of epochs. Epochs meaning number of iterations. This is an arbitrary number, you can choose whatever you want. But of course, only doing this for one epoch is not going to do that much. Alright? Especially if you're doing only stochastic gradient descent. So for a certain amount of epochs, compute the error. Then computes, right, this is the function for the error. Then computes the partial derivative theta L to your theta of each and single one of your variables. Then subtract that partial derivative from your current value, right? And then now you have a more optimized function. Repeat again. So that's really the pseudocode. Now let's do this again. For, let's say, and by the way, when I say compute error here, I'm thinking of more a batch gradient descent, which means we go over the error of every single data point, and then we compute it, instead of stochastic, which is only taking one data point and computing the error and then going on to the next data point. So this is going to compute the entire error of all of the predicted y's and the actual y's. And then we're going to compute the partial derivatives of those laws in respect or with respect to the individual variables that we have in our equation. So in this example, right, we only have theta 1 and b. Then we're going to edit that value from our current value, and then of course now our machine learning model is even a little bit more accurate, and that when we compute the error again, this error should be a little bit less than the one last time, and then we repeat until this error is really low. Yeah, so that's it for this video. Thank you for watching. In the next video, I should be going over neural networks, but if not, I'll probably be going over of implementing this thing right here in a machine learning library, or maybe even just a basic Python vector manipulation code. So see you guys next time.